Everybody, my name's Nicholas. I'm the UAV coordinator at Land Surveys. I sort of made this presentation without realising that I'd be dealing with a sort of more informed audience, so if it's a little bit basic for everyone, bear with me. The upside is that I've got plenty of pictures and stuff. I wanted to, Dan asked me to do the presentation on LiDAR, but I wanted to put everything into context, so I just wanted to cover a little bit about, the recent advances over the last 10 years in photogrammetry, and just tie it all in together. So over the, as probably a lot of people know, over the last few years, UAVs have become parts of businesses and workflows and in surveying, partly due to changes in batteries and sensors and everything like that, and GPS and things like that. So we're going from we're sort of blending the capture sizes of conventional aerial survey and LiDAR and to UAV survey. So and basically it's just a question of scale as a factor of weight. We're doing UAV surveys that are getting bigger and bigger, and sort of the distinction between conventional fixed wing capture and UAV surveys is becoming less. So I think probably I don't really know the time frame when computer vision started to become a part of the survey workflow, but to draw a timeline of it would be sort of doing heads-up mapping vector capture and having very rigorous camera models and stereo pairs, to throwing bunches of images into a computer and using computer vision and techniques like sift and ransack in order to create dense point clouds. And obviously, going back a little bit before that, you've got direct georeferencing adding to that sort of workflow in a hardware sort of sense, and then obviously LiDAR coming into that as part of a direct measurement rather than a calculated measurement. So you can't see the top, but it actually says processing workflow, and basically the most important part of any aerial surveys and planning and the project design, and making sure that you know what's required and how you intend to go out and meet your specification, and then actually to going out and doing the work, and then breaking it down into the processing in terms of doing the trajectories, calibration, clipping the trajectories, color-lining the swaths, colorizing the point cloud, and then applying the geo model, tiling and classification, removing ground and non-ground, removing non-ground features, and then quality assurance. So in terms of project design, you're looking at accuracy as a factor of flying height and speed for a LiDAR workflow. So based on the type of requirement, what type of control you put in, the distribution of the control, how high you're going to fly to capture the data, and the speed at which you're flying as well. And obviously, what's going to sort of, I'm assuming that a lot of people have dealt with aerial survey data sets, but where the sort of the RPAS-based LiDAR data set comes into it is, and really sort of just distinguishes itself amongst the current technologies is in the detail, the accuracy, and the point density. So this is pretty, this is pretty standard stuff. We process the trajectories using PBK as opposed to RTK, although there's pretty good RTK systems out there. But the advantages of PBK is that you can do backwards and forwards processing. The satellite ephemeris, and you process the trajectories to get what's called an S-bet, which you can see on the diagram, which is really clear. But the S-bet works on relies heavily on physics, because obviously the GPS is a noisy measurement, and the physics of calculating through gyros the orientation, the velocity, and other inputs that you could put, for example, in a mobile mapping system, you throw other measurements like odometer readings and everything like that, so that in GPS poor environments, you've got a model so that you can integrate that with the GPS measurements to refine the position of the aircraft, and obviously the accuracy of the final data set. So this is probably the nuts of it, and where the accuracy really lies is really based on the quality of your IMU measurements. So at this stage, we're just looking at sort of resolving any GPS outages, inputting the lever arms, and making sure there's no problems in the capture process. So if you've been working on a Sunday and you've got rollover week and or your image timestamps are out, you'd resolve them at this stage. Or if you've got a problem with your the positioning of your sensor on your aircraft, this is where you'd sort that out. And then sorry, I've sort of skipped a little bit here, but as I try to keep it sort of software agnostic. So there's an intermediate stage where you've got your trajectory and you're outputting your LiDAR returns. And once you've got so you're going from trajectory to point cloud. Once you get your point cloud, you're doing a strip adjustment, so you're flying in parallel lines and you're co-aligning your swaths, and or doing a calibration at the same time to make sure that the overlapping points mesh in nicely with each other into one contiguous block. And there's a lot of softwares now, for example, Regal or like a mapping suite, allow you to input the control positions in the creation of that block. On the other hand, you can also do that outside of this process as well. And then the next step is classifying the point cloud. And this is just a standard ICSM class. There's a lot more classes in different kind of specs that you look at, but as a basic sort of classification structure, we're looking at putting all of our ground returns onto class 2, and low vegetation we're separating into the distance of the surface to points above different increments. So the advantage of LiDAR is in the multiple return technology, which this diagram pretty much explains the advantages of that. So basically, you've got a very fast spinning laser, and you're measuring the time the pulse gets before from when it's sent out to when it's returned. But each pulse has multiple echoes. So for example, when that pulse hits a tree, it'll create one echo, and then when it hits the ground, it'll create another echo. That allows you to really quickly and easily filter out ground and non-ground terrain. So this is basically an example in cross-section view of the you know, the effects of that multiple the waveform technology, where even in pretty dense vegetation, this was in Borneo, we're getting a really nicely defined ground surface with a lot of returns. So I've got a few examples of some recent projects. So this is just a, you know, a LiDAR project that we did from UAV, and we captured at a really high point density. So by flying really low to the ground and really high overlap, and tying it into MLS data. So, you know, our RMSs were really good. So it was, you know, sort of plus or minus in the 20 to 30 mil range. And you can see that the detail of the capture there, and what the classifications quickly. Oh, it's 92. I'll move on from that. Oh, here we go.
What's your aircraft?
M600. So I just wanted to classification. So yeah, I've just removed the non-ground features. So there's a lot of detail in here. There's a drain in here that would have just been, you know, a nightmare to walk and really heavily vegetated, but you know, we've modeled it fairly well. And, you know, the pressures. So I just, and I just wanted to look at another data set here. Just refresh that as well. So this is, so I just turn the vegetation off. So this second data set is actually a photogrammetric point cloud. But the classifications work just as well. And I suppose that's what I wanted to put into context the different sort of applications. So, you know, because obviously the sensors are smaller with the photogrammetric sensors, you can fly a lot more, fly a lot longer, and achieve a, you know, a fit-for-purpose result. Whilst the LiDAR's, you know, a lot heavier, whilst it achieves a more accurate result, and I don't want to use the word better, but more detailed and comprehensive data set. You know, they both have their place because you know, in a day with a fixed wing aircraft UAV, you can capture probably about 600 hectares, whereas with a LiDAR, it'll be half that on a UAV. And you know, the product's not too dissimilar. You know, so it's really, you know, we're just talking about scale and coverage and really economics about what you want to capture. The other sort of point is there are limitations with photogrammetry. You know, you've got to fly during the day. You can't penetrate through vegetation. Shadow impairs the accuracy of the model, and homogeneous terrain, such as, you know, roads, will have a lot of noise in them and aren't suitable, you know, for modelling. So you won't, you know, point clouds from photogrammetry we really only do for natural surface and not built structures. Whereas you don't get any of those problems with a LiDAR data set. Another example is you know, beach sand and sand dunes, because it doesn't have any texture and everything looks similar. From a photogrammetric point of view, there's going to be a lot more noise and a lot more inaccuracy in that data set. So this is an example we did over a sand dune, and you can see the photogrammetric data set sits up about sort of 8 centimetres high of the LiDAR data set. And you can also see in the white, there's a lot more, you know, there's sort of 100 to 150 mil of noise in the photogrammetric data set, whereas the LiDAR data set's quite clean. So that makes it really, you know, really suitable for power lines, roads, infrastructure, and all that kind of, you know, ASCONs and those type of surveys. That's pretty much it. Are there any questions?